We will now calculate the mean value and dispersion using the Gaussian distribution. I have here included the review of mathematical notes that could be of use in this calculation. So let's start with the mean value. So first of all, what was the Gaussian distribution? The Gaussian distribution is P as a function of n, probability distribution. It is 1 over square root 2 pi npq, capital NPQ, exponential minus 1 over 2 n minus np squared divided by npq. So this is our Gaussian distribution. Now, how do I calculate the average value or mean value? It is going to be n bar if n is a continuous variable, in which case we use the Gaussian distribution. It's going to be the integral over all possible values of n, n p of n dn. So this is the definition of the average or mean value for a continuous variable. You multiply it with its probability distribution and integrate over all possible values. So with that, the mean value of n is going to be 1 over square root 2 pi capital NPQ integral from minus infinity to plus infinity exponential minus n minus capital NP squared divided by 2 NPQ n dn. So here I'm going to basically recall that this np was the most probable value. It's the maximum point in the probability distribution. So I'm going to call n minus n tilde, which is capital NP, as a new variable y. So I'm making a change of variables, and with that dn is going to be equal to dy. So the mean value then becomes 1 over square root 2 pi npq integral from minus infinity to plus infinity e to the minus y squared divided by 2 npq. And now for n, I'm going to substitute. So as you can see here, n is then y plus n tilde. So it's going to be y plus n tilde dy. I have changed dn to dy. So there are two parts to this integral. So for the mean value of n, I have the first part 1 over square root 2 pi npq integral from minus infinity to plus infinity e to the minus y squared divided by 2 npq y dy. And then I have the second part 1 over square root 2 pi capital NPQ integral from minus infinity to plus infinity e to the minus y squared over 2 NPQ and tilde dy. So I noticed that here I have the Gaussian term. So this Gaussian term is an even function, and this y term here, that's an odd function. So what does even function mean? If you look at f of minus y, it's equal to f of y. That's even function. F of minus y is minus f of y if it's an odd function. So if you have the product of an even and odd function and you integrate over the whole range of values from minus infinity to plus infinity, this is going to give you a 0. You can prove it to yourself if you wish explicitly using these, for example, using this one, integral from 0 to infinity e to the minus alpha x squared x dx, that's equal to 1 over 2 alpha. So you can perform this integral from minus infinity to plus infinity. You will see that it's the integral from 0 to infinity, and infinity to 0 if you look at the values that y should take when n goes from minus infinity to plus infinity. So recall that this minus infinity plus infinity is for n. So this is for n. And we're going to see that the second part will have a contribution. So for the mean value of n, we will have, by recognizing that alpha constant is 1 over 2 npq, I can write this as n tilde, which is np, divided by square root 2 pi npq, integral from minus infinity to plus infinity, e to the minus alpha y squared dy. What is the integral of e to the minus alpha y squared dy from minus infinity to plus infinity? That's here. It is square root pi over alpha, so I substitute that, capital NP divided by square root 2 pi capital NPQ, and then I have square root pi over alpha, so here is my alpha. What is square root pi over alpha? Let me calculate it. It is square root pi multiplied by square root 2 npq. So it's going to be equal to square root 2 pi npq. So I substitute that here. Square root 2 pi npq is the result of the integral. So these two will cancel, and I find at the end for the mean value n bar, it's equal to n tilde, which is capital N P. So the mean value and the maximum probability value n tilde are the same. Now I would like to calculate the dispersion for the Gaussian distribution. So let me remind you, delta n square bar, the dispersion is the deviation from the mean squared average. So this is going to be, by definition, the integral from minus infinity to plus infinity, n minus n bar squared probability distribution dn. So that's the definition of the dispersion. So if I substitute here the probability distribution, so delta n square bar, the dispersion will become 1 over square root 2 pi capital NPQ, integral from minus infinity to plus infinity, the Gaussian e to the minus n minus capital NP parenthesis square divided by 2 NPQ, and then I have n minus n bar, which is capital NP, square dn. So this time I'm going to call n minus capital NP y, so that dy will be equal to dn. And with this change of variables, this is going to become 1 over square root 2 pi capital NPQ integral from minus infinity to plus infinity e to the minus y squared divided by 2 NPQ and then y squared dy. Okay, so then I recognize that 1 over 2 NPQ is a constant. 1 over 2 capital NPQ is my alpha. So this is basically 1 over square root 2 pi capital NPQ integral from minus infinity to plus infinity e to the minus alpha y square dy. And the question is, do I know what this integral is? So I look at my integral values that I calculated. So I have this relationship between I2 and I0, so that's what I'm going to use. So I know that the integral, so this is basically reminding myself what I know about these integrals here. I know that this integral I sub 0, the integral from minus infinity to plus infinity, e to the minus alpha y square dy, this integral is 1 over 2, well, for minus infinity to plus infinity, there is no 1 over 2. It is square root pi over alpha. So this is square root pi over alpha. Then I know the following. The integral of n for x, that includes an x to the n term, is n minus 1 over 2 alpha integral n minus 2. So what I need here is I2. It is 2 minus 1 over 2 alpha I0. So this is going to be equal to 1 over 2 alpha multiplied by I0. That is square root pi over alpha. So this is going to give me square root pi over 2 alpha to the power minus 3 over 2. So that's the result of this integral. So I'm going to get here for this one, the dispersion delta n square bar will be equal to 1 over square root 2 pi npq, capital NPQ, and for the integral minus e to the minus alpha y square dy, I substitute square root pi over 2 alpha to the power minus 3 over 2. So alpha was 1 over 2 npq, so it is 2 and capital NPQ to the power 3 over 2. So square root pi's will cancel. So let's see here. I have square root pi in the numerator. I have 2 to the power 3 over 2. Then I have NPQ to the power 3 over 2. In the denominator, I have square root pi, I have 2 to the power 3 over 2, and NPQ to the power 1 over 2, that's square root. So this one will go away, this one will go away, and then as a result I will have here just capital NPQ. So the dispersion that I calculate using the Gaussian distribution is capital NPQ. so that the standard deviation is square root capital NP Q. With this, we can basically recognize that the Gaussian distribution P of n is 1 over square root 2 pi, the standard deviation, delta n, exponential minus 1 over 2, the deviation from the mean divided by standard deviation, parentheses, squared. Or if you wish, you can write this as P of n multiplied by the standard deviation is 1 over square root 2 pi e to the minus 1 over 2 z squared, where z is the ratio n minus n bar divided by the standard deviation. So that's another way to write it, but it's the same thing. So that's the form of the Gaussian distribution here. That comes out of this calculation. So just to recap what we have done here, I have used the Gaussian distribution for a continuous variable or approximately continuous variable n. And remember the conditions under which we can use the Gaussian distribution. Let's note here n has to be much greater than 1. It has to be a large number and not close to capital N also, and we're looking at the distribution near n tilde basically, which is capital N P. So under these conditions and probability P and Q should not be equal to or close to 0, so that I have the Gaussian distribution becoming valid as an approximation for continuous distribution. Binomial distribution represented by Gaussian distribution for a continuous or approximately continuous variable. And remember, the binomial distribution has to be a smoothly varying function, so that you should have Pn plus 1 minus Pn should be much less than Pn. So that's a smoothly varying function. These were my assumptions. And now the Gaussian distribution is 1 over square root 2 pi capital NPQ exponential minus 1 over 2 n minus capital NP parentheses squared divided by NPQ, as we have shown in the previous videos. And by using the definition of the average value, that's integral from minus infinity to plus infinity, the variable multiplied by its probability integrated over all possible values, I have shown that by using the integrals of the Gaussian and integrals of the form Gaussian multiplied by x to the n, the mean value is capital NP and the dispersion is capital NPQ. And the standard deviation is square root NPQ, so which led me to figure out that the Gaussian distribution is actually 1 over square root 2 pi standard deviation exponential minus 1/2 deviation from the mean divided by standard deviation squared.